Alright, so for our next problem, we have a merry-go-round problem. And Jim, Susan, and Jumbo are riding the merry-go-round, and it has a 10-meter diameter. Jim is pushing clockwise with a 20 Newton force, Susan also pushing clockwise with a 30 Newton force, and Jumbo, bless his heart, is dragging his feet while sitting and causing a 10 Newton friction force counterclockwise. So, good old Jumbo just enjoying the ride here. Now, we're going to ignore Jumbo's weight because technically with him sitting on this merry-go-round, that would affect the moment of inertia. So we're just going to neglect his weight at this moment, though probably shouldn't for how much Jumbo weighs compared to the merry-go-round. But for the purposes of this example, we're going to find the moment of inertia of the merry-go-round. So we'll just go ahead and underline some of this key information, draw the picture. 10 meters, and you've got Jim and Susan at their locations. It says that they're riding, so we're going to ignore their weight on it too, I guess. He's pushing it clockwise at a 20 Newton force. Susan at a 30 Newton, and Jumbo in the opposite direction, dragging his feet at 10 Newton force. So the first question just says, find the moment of inertia of the merry-go-round. Once again, we're going to model this merry-go-round as a disc or as a cylinder. So from the textbook, we have that formula, 1/2 mr squared. That is 1/2 times the mass times the radius squared. We end up with a moment of inertia of 1,875 kilogram meters squared. Next, find the net torque on the merry-go-round. Which way is it rotating? Okay. Well, we probably have a good idea that since Jim is pushing with 20 newtons, Susan with 30 newtons, and Jumbo is just sort of dragging his feet, just looking at the forces and assuming they're pushing at the edge, which they are, we would assume that the merry-go-round here is going to be rotating in a counterclockwise, or sorry, in a clockwise direction, which would be a negative value. But we're going to, just to be sure, we're going to add up all the torques here. So the net torque is the summation of all the torques. Jim pushing in a negative direction, Susan in a negative direction, and Jumbo in a positive direction. In this case, we'll assume naturally that all of their forces based on the picture here are at a 90-degree angle. And as you recall, the sine of 90 degrees is 1, so that's going to affect our calculations. It's going to make it nice and easy. So the negative torque due to Jim, negative the torque due to Susan. We're just identifying those as negative, just as a reminder here. So negative the force times the distance times the sine of theta. So 20 newtons at a distance of 5. Putting it at a distance of 5 because the diameter is 10, but the radius there is 5. Times the sine of 90. For Susan, subtracting that there, 30 times 5 times sine of 90. Plus Jumbo, 10 times 5 times the sine of 90. And we end up with a net torque of negative 200 Newton meters, which tells us that we're going clockwise. We figured that out in advance, but it's nice that the math gives us a negative answer, which would indicate clockwise rotation. So it's nice that that validates our prediction. Part C. Calculate the angular acceleration alpha. All right, well, Newton's second law of rotation yet again gives us this nice formula, net torque divided by moment of inertia, which happens to be, yet again, the first two items that we were given, or that we were asked to find in parts A and B. So we do that division, and it turns out to be negative 0.107 radians per second squared. Part D. Assuming the merry-go-round starts from rest, which means omega naught equals 0 radians per second, how long does it take to speed up to 1 revolution every 2 seconds? That's actually really fast. So it's going all the way around 2 seconds. This is because Jim and Susan are constantly applying their force here. So we're gonna, that 1 revolution every 2 seconds, that is an angular velocity. That's omega. That's omega final. So write that as 1 revolution for every 2 seconds. We don't like revolutions per second. We want radians per second. So we'll do a quick little conversion there to cancel out the revolutions. And the turns out to be actually pi, or 3.14 radians per second. So we now have an omega naught, and we have an alpha from part C. So we need a formula that's going to relate those three concepts along with time, and we have that. It's omega equals omega naught plus alpha t. That's one of the formulas on our formula chart. Solving for t, which means subtracting omega from both sides and then dividing by alpha, ends up with this formula, omega minus omega naught over alpha. We can just plug in our values and end up with a nice number, 29.5 seconds. So about half a minute of their force, of their applying that force there. Now once it reaches this speed, what is Jumbo's velocity, assuming he's sitting on the very edge? So once again, when it talks about velocity, we're not talking about angular velocity, how many angles or degrees or radians is he going through, but rather sort of like how fast is he going? You know, what it would be the distance that he would travel in a given time. And so there's one of those linking formulas again. It's velocity equals r times omega. Now this is once he's going at that speed, that omega of 1 revolution every 2 seconds. So that's the omega that we're interested in. So it's going to be 5, which is the radius, times that pi, radians per second. So it turns out he's going to 15.71 meters per second, which that is very fast. Hopefully Jumbo is able to hold on to that. So very interesting result there. You can see once again just applying these formulas, plugging in the values. Thanks for watching.